Our next presentation is by Dr. Daniel Althoff. He's at Stockholm University, and the title of his presentation is Explainable Machine Learning, a Peek into Black Box Models.
So, hi everyone, can you listen me well?
Yes, we hear you and see you too, thank you.
Okay, so my name is Daniel Althoff, and today's presentation is about explainable machine learning. And the main objectives of this presentation are to outline some of the methods used to improve the interpretation of machine learning models and present a case study where these models are applied. So I'm not going to get in a lot of details behind the explainable machine learning methods, but I'll provide the references. And this case study is not from any work in particular, but it was developed using data from which I collected during my PhD. So just to cover the basics, I know you guys already know this, but machine learning, according to the IBM Cloud Education, machine learning is a branch of artificial intelligence and computer science which focuses on the data and algorithms to imitate the way humans learn, gradually improving its accuracy. And according to Expert AI, it's an application of artificial intelligence that provides systems the ability to automatically learn and improve the experience without being explicitly programmed. So what we usually have, we're going to have a set of input variables, which can also be called features, predictors, or covariates, and we want to predict an output variable. And we use these machine learning models that learn automatically, this in a supervised scenario. And we want them to do as best as it is possible. But then comes the question, why is it important to improve our model interpretability? Because when we use machine learning models, they are frequently seen as black box models, which are models that do not reveal its internal mechanisms, or models that cannot be understood by simply looking at their parameters. Let's say you use a multiple linear regression, you can very straightforwardly look to the coefficients, and then you have an idea of what's going on, but that's not how it goes for machine learning models. So the models, they learn automatically and they may have complex structures, so it is important for us to know what's going on behind the curtains. They are usually chosen based on performance, and the model may poorly predict some certain situations. So if we can look in of what's going on, we can maybe find sources of ineffectiveness and improve our model. And it can also be used to increase our domain knowledge and build trust on model robustness, as has been discussed in the previous presentation. For example, if we can reconstruct unknown parameters, and then we have characteristics for watersheds which we previously didn't know. And for the responsible use of machine learning, because if the model you developed is used for decision making, it is important that you know why it's making such decisions and be responsible for it, because it may affect people's lives. And explainable machine learning, for me, they are methods that are used for visualizing, interpreting, and explaining machine learning models. So they are also sometimes referred as explainable artificial intelligence, but then it's the use of explainable artificial intelligence in the subdomain of machine learning. And there are different definitions I've seen over time for what's explainable or interpretable model, and the ones I think that are most suited are that interpretable is the degree to which a model can be understood. For example, linear models are can more easily be understood. They're more interpretable, as are decision trees. And then we have, for example, deep neural networks, which are difficult to interpret. And the explainable is so you can use additional methods to understand how the model works, as we have been seeing the last 2 days in this workshop. So you see what it does, but can you explain why it does? And for the explainable machine learning methods, We have some models that are interpretable by design, so they might not need explainable methods to aid them. For example, linear models, you can look at the regression coefficients, you can look for decision paths in decision trees, and so on. But there are other models that may have more complex designs. And for these models, the explainable methods, they can be model specific, which takes in consideration the structure of the model for whichever explanation task they're doing. For example, to assess variable importance in linear models, you can look for the t statistic, and for random forests, you can check the decrease in node impurity to see how assess the importance of these variables. And they can also, these methods can also be model agnostic, so they're independent of any knowledge of the internal structure and works on any predictive model. In this method, they can also be directed to a single observation, say, so they would be a local explanation task, or they can be directed to the whole data set. It would be a global explanation task. And I'm just going to present a few of the methods, the ones I am more familiar with, and their reference, and whether they're global, model specific, or model agnostic. So, for example, the first one is the variable importance. It's a global explanation task, which can be either model specific, as mentioned in the previous slide, or model agnostic, using, for example, permutation-based approaches. There is a partial dependence profiles, which profiles the global behavior of the model, the global behavior of the model in context of a single variable or a pair of variables. It's a model agnostic, and it's a global explanation. So you have a general expectation. If you change one variable, how much is it expected to change the prediction? There is the individual conditional expectations, which is also model agnostic, but it is local. It's very similar to partial dependence profile, but you zoom in a specific case, in a specific instance, and for this one variable, you change it and see how the model is expected to respond. There is also the local interpretable model agnostic explanations, which, as the name says, it is local and model agnostic, and it uses surrogate models to see the feature attribution on the prediction. And there's the Shapley additive explanations, which is a local and also model agnostic. It uses game theory to compute Shapley values, which are used to also see how the features attribute on the prediction. And you can also use it in a global way if you just gather the attributions for all the features for the entire data set. You can have the aggregated chat and see just have the general, a global explanation. And there are other model specific ones that we have been seeing in many of the presentations for neural networks more specifically, and there are many different ones. I just give two examples here, the integrated gradients and the layer-wise relevance propagation. But in this presentation, I'm not focusing on neural networks, so I'll have a greater focus on these first ones, which are model agnostic. So the case study, I used the Hidro Cerrado dataset. It's a regional sample dataset for catchments within the Brazilian savanna biome. It's a dataset I put together during my PhD. It has data for 411 catchments with at least 5 years of stream flow observations between the years of 2000 and 2015. And the objective of this case study is to create a machine learning model able to estimate a low flow hydrological signature from catchment attributes. And this low flow hydrological signature that I'm predicting is the Q95. It's the flow that is equal or exceeded 95% of the flow record. And so this would be like creating a model that can be used to regionalize this hydrological signature. And it's a signature that's strongly related to flow levels during the dry season. So it's frequently used in Brazil as a reference for granting water rights. And well, that's our objective. So we can create a model and predict the signature in places that are unmonitored or ungouged. The machine learning model that I chose is the cubist regression. it's based on regression trees, and it uses a boosting like scheme, but instead of in regression trees, instead of having these discrete values in the predictions in the final nodes of the tree, it has linear models. So it's a really interesting machine learning model, and I've had a lot of successes in it in the past, having a performance similar, for example, to random forest, sometimes even better, and usually trains faster. The setup, I used 80% of the catchments as the training set and 20% of the other 20% as the test set. And for hyperparameter tuning, I used the repeated k-fold cross-validation. And to interpret or explain the model, I used the following methods, which are the variable importance, the partial dependence profiles, individual conditional expectations, and Shapley additive explanations. And here in this, as this slide, my entire presentation was written in R, and there are some code chunks, so maybe this presentation can be useful to some of you in the future. So here is just the data set, the range values for each of the variables. So here Q95 is our target variable, and then we have the average annual rainfall for the catchments, average minimum motif evapotranspiration, a seasonality index, which tells you whether the evapotranspiration and rainfall peaks in the same period or if they peak in opposite seasons. We have some soil characteristics from the soil grids data set. There's the log transformed area, average slope of the catchment, average elevation, and some land use cover characteristics from the Map Biomas project, which is a data set for land use cover in Brazil. So first I split the data into training and test sets. So we have 328 catchments in the training set and 83 catchments in the test set. And then I use the carrot package to train the model. And our test set performance is a Nash-Sutcliffe efficiency of 0.68 and a Klein-Gupta efficiency of 0.78. So the model did all right, and I know we can likely improve this. We can test different models. I used the default tuning grid for the Cubist model, and we can do better than this. We can even try feature selection or feature engineering. So this is just I'm going to focus on the explainable methods and not waste too much time here in the training phase. So let's speak into the black box. First, the variable importance, still using the carrot package, we can compute it in different ways. It allows us to use the model, so it would be a variable importance using a model-specific method. And for the Cubist regression, here it assesses how many times a variable is used in the decision paths or in linear models recursively up the tree or trees if you use the boosting-like scheme. And for some models, you might not have the model-specific way to check the variable importance, so you can use the model agnostic. The carrot package in particular assesses the relationship between the input variables, the features, and the target variable, and this can be done using a linear model or local regression. So when we check for the variable importance, we can see that they have a similar pattern. Some variables got a different outcome, for example, for the model agnostic or specific methods, for example, pasture or bulk density, silt, and a little bit difference in other variables. But we can see that the variables that are considered the most important are generally the same. It's rainfall, it's the evapotranspiration, the seasonality index, slope, and from the fraction it would be like grassland, pasture, or savanna formation. And there's another package that we can also check the feature importance, and this package is the interpretable machine learning. And this package it's pretty good, and I use it for the following explainable methods in the following slides. I also use this package, and here I'm just using the model and the data set, and the way it computes the feature importance. It shuffles each feature at the time and see how much it increases for example, the root mean square error, where you can use a different loss. but in this case, it's going to shuffle the features and assess how much it increases in the root mean square error. So let's say if you shuffle a feature and it increases too much your error, it means this feature is important. So the outcome that we have is this one, and you can see it's fairly similar to the other two methods. So, but this one is a model agnostic. You can use this for any machine learning model. The next one I'm going to show you guys is the partial dependence profiles and individual conditional expectations. They can be computed all at once because they are quite similar. And this I'm doing for a single feature, which is the seasonality index. So here, first we have this, the black lines, which are the individual conditional expectations. It's the profile for a single observation. If you grab a single observation from your data set and you change your seasonality values, that's how you expect your prediction to change. And this black bar here is in the bottom. They show where the data usually concentrates. So it's the regions where you have a higher confidence on how they retain changing. And the yellow line would be the partial dependence profile. It's the global for the entire data set. It's the global behavior in the context of this, when you change seasonality, how it changes the prediction. And you can do this for all the variables. For example, for all the variables that we used. And here we can, it's just interesting how you can maybe learn something new or just check if whatever you've seen makes sense with your previous hydrological knowledge. So let's say when we increase the slope, we usually have higher direct runoff, so less recharge. And then in the dry season, we're going to have lower flows. So when we have a higher slopes, we usually have a lower Q95. As for example, for having the higher percentage of sand particles, it's expected to increase Q95 because soils with a lot of sand usually have a higher infiltration rate and can have a higher recharge. But we see a similar behavior for clay, which is interesting because in the Cerrado, the Brazilian savanna, the soils are really old and well structured. So even when you have a high percentage of clay particles, you're still going to have this high infiltration. You're usually going to have a high infiltration. So it's interesting to see that even when clay increases, it increases the recharge and likely increases the recharge and increases the flow under low flow conditions. So we would have a higher Q95. And then we can see it's expected to increase when we have a higher rainfall or decrease with lower evapotranspiration. We can also look at this in the context of different land use covers. For example, grassland and pasture, they are generally very similar, but for this data set, grasslands are the natural formation. So they usually have less evapotranspiration than the forest fractions, but as a natural formation, they likely have a higher infiltration than pastures, because pasture, for the most part in the Cerrado, we see a lot of degraded pastures, which will make it so you have a higher direct runoff, less recharge, and less lower flows during the dry season, as opposed to grasslands, which can help you with the recharge and higher flows during the dry season. So you can just keep going on and checking if this makes sense with your previous hydrological knowledge and see the global behavior. I've even seen people trying to use these global behaviors in symbolic expressions, so you can have a general model that's more interpretable. There's another package that can also be used for the partial dependence profiles and individual conditional expectations. It's the package PDP. And this is basically the same thing we've seen in the previous slides. The black lines here are the individual conditional expectations, and the red lines the global behavior, the partial dependence profile. And this is for the penetrative evapotranspiration, where we can see that when we have a higher evapotranspiration, we're going to have lower flow under low flow conditions. But what I like about this package is that you can look at this from a different perspective. You can have centered plots. So here, if we include the center and make it true, it's going to look from the same point of view. So we can see how it usually changes. And of course, for the different catchments, there are a lot of other interactions but it allows to create these centered plots. And it also allows us to see the partial dependence profile in the context of more than one variable, for example, the interaction of two variables. So here, let's say for the seasonality and penal motif. So when we increase the evapotranspiration, we're going to have lower Q95, and as well when we have a higher seasonality, closer to 1, it means that if the evapotranspiration peaks in the same season as rainfall over the year. So most of soil moisture is evaporating and not going to percolating to recharge water table. So we can see the conditions that lead us to a lower prediction of Q95. And for the last one is the Shapley additive explanations. This first example, I'm just using the third observation in the training set. And this is how the features attribute on the prediction in relation to the average prediction. So 0 here would be the average prediction. And for this specific case, we have what for the Cerrado is a low rainfall, which is 1,000 millimeters a year, and it attributes negatively on the Q95. We have a very high evapotranspiration of 1,700, so it also attributes negatively on the Q95 in our final prediction, as opposed to Payshers, which we've seen that Payshers, a high Paysher fraction as land cover can decrease our Q95, but here it's only 2.6% the fraction, so it attributes positively. And then we can aggregate this to the entire data set, and we have just a global picture of what our model is doing. And here we can see for each variable, if the feature values are high or low, and how they are spread, and how it changes. So here it's quite interesting. If we see this large spread, high variability means that your model has a higher importance and can have a higher attribution on your prediction. So this is if we rotate this picture, it would be similar to the variable importance plots I showed earlier on. And what we also like to see here is this nice pattern for the colors. So you can instinctively see that lower rainfall is going to attribute negatively on Q95, while higher rainfall is supposed to attribute positively. And so this is just a really straightforward way. You can even zoom in a single variable and create a plot and see if this is somewhat skewed or not. And I've seen people starting to use the Shap method for feature selection. For example, if we see the variables that have a short variation here, they usually have a lower importance, and especially when the colors are all clumped up, it may be that this variable is only adding noise to your prediction, so you could remove these variables, or you can see that they have predominant color. Maybe your data is skewed, and maybe you could work on some feature engineering and look for better results. Or if the colors are all mixed up together, maybe it's trying to memorize what to do when you have this specific outcome. It's not what you want. You want it to have to capture the general behavior. So this is all I put together for you guys today. These are the reference from the citations I used, and I thank you guys for the opportunity to be here and present this. And I hope you guys enjoyed it. Thank you very much.
Yeah, thank you, Daniel. That was excellent. I think you give the hydrologists among us a great deal of, I guess, incentive to look into these methods, and of course, the machine learning, the computer scientists as well, I believe. But I look forward to trying some of these methods. Now, I don't see that there's any questions right now, but if anybody comes up with questions, you can still add them even later. So I think we should move on.